Hi you guys, welcome to your first Honors Math 3 video lesson. All of your Honors Math 3 stuff will not be via a recorded lesson, but this is one lesson that I do want to have you guys do. So I know it's not ideal, but we're gonna figure it out, work through it. So you will need a couple of things to start off this lesson with. I have attached this file for the 1.2.2 resource page. So that was in the Honors Math 3 folder on Schoology. You'll also need to get your book out. I will be referencing a problem in your book that we're going to do together. So we're going to be on lesson 1.2.2. So get your book out, turn to page 33, and you can reference that, have that next to you ready to go. Okay, so on problem or lesson 1.1.2, this whole lesson is on modeling a geometric relationship, which is really important to see as a math student. I like it because it does show you some practical applications of some of the stuff that we learn in math. So we're going to model a situation. So I'm going to read through this intro here. So mathematics can be used to model physical relationships to help us understand them better. In this lesson, you will analyze a geometric relationship and look for connections among its multiple representations. You'll be given a geometric situation to explore and analyze by gathering and interpreting data. I will be giving the data for you. Then you'll generalize your findings by creating a mathematical model so that you can make predictions. So mathematical models are basically equations that represent something that's real, so that you can use that equation to make predictions about different scenarios. So what we're gonna do, I'm gonna walk through problem 73 with you guys and have you follow along and show the same work that I work through on this resource page. So obviously it refers to your team. It's not gonna be your team since you're just following along with me, but we're gonna make several paper boxes, and based on the physical models, we will then represent the relationship between height of a box and its volume. So that's the big idea here. So it says to cut a sheet of centimeter grid paper. So I will show you, I've got lots of centimeter grid paper. And I'm just gonna explain this to you guys without sharing. So what this problem says, you could even pause and read through the problem if you want, just so you have a better view of it, but I'm gonna kind of just break it down for you now. So the idea of the problem is if you're given a set size, like imagine I hand you a board, a large flat board of wood, and said, I want you to build me a box with the largest possible volume, but this is the only material you have to work with, this big giant flat board. You have a lot of different options for dimensions of that box. You can choose a height of 1 inch, 2 inches, 3 inches, 4 inches, 5 inches. So the idea of this problem is, how does changing the height of that box affect the volume of the box if we are hoping for the largest possible volume? So we're going to use this to represent a large piece of board, but it's just a small representation of that using paper, so we can kind of model it with paper. So let me pull the problem back up here. So you can see in the image right here with this rectangle with the corners here, to form a box from a rectangular piece of material, you would cut whatever height you want, you would cut out of the corners, and then imagine folding those up so that those where those corners are now removed, that's where that would become the edges or the corners of the box. So that would form this box here. So we are working with this first dimension here, 22 by 16. So imagine a large piece of board with a set dimension. So we're going to represent that with a 22 by 16 centimeter piece of paper, and experiment a little bit and see how that height will affect volume of the boxes. Okay, so in problem 74 right here, this is going to walk us through what I'm going to demonstrate for you. So we're going to begin our investigation by building several boxes, taking measurements, and collecting data here. So as a team, choose a starting input value for height of the box. So what that means is, let's imagine I have this material and I say, all right, what's the volume of my box if the height is 0 centimeters? What's the volume of my box if the height is 1 centimeter? And so on, and we will calculate each of those situations. So I'm going to show you what I'm looking at here. So using my document camera, we'll work through this, and our paper dimensions, like I said, this is what I'm working with. A piece of paper that is 22 by 16 centimeters. So that's going to be our original dimensions here. So 22 centimeters by 16. And those values are going to come in handy for us. I'm going to put my name on this because I'm going to ask you guys to submit your work today that you've done with these notes. Okay, before we start with choosing box heights, let's review volume of a rectangular solid. So the volume for an object with a rectangular base is just length times width times height. So that's going to come into play here because we know our box is 22 by 16. So what that will help us determine, we'll know the length and width based on the height. Okay, so let's just start with, like I mentioned, if we have a height for our box of 0 centimeters, then when we calculate the volume of that, since the height would be 0, the length times the width would be 22 times 16 times 0, which of course anything with a height of 0 has a volume of 0 as well. So that's kind of seems silly to start with, but we just want to make sure we look at all of our options. So now let's think about a box with a height of 1. So that would mean, with my paper here to represent this, if this is my starting piece of material and I want to figure out what the volume would be with a box of height 1, that would mean I would need to cut this corner out and fold up, cut this corner out and fold this edge up along this line 1 centimeter in, and that would form the edges of my box. So I'm going to pause and do that now and show you the result, and then we'll determine the volume of that. Okay, so here is my little shallow 1 centimeter height box. So let's talk about the dimensions of this. In terms of length and width, remember the original length of here, we'll call the length the shorter side, was 16. But since I cut a 1 centimeter corner out of each of those sides, I lost 1 centimeter over here and 1 over here. So instead of a width of, or a length of 16, now I'm looking at a length of 14. And likewise, instead of a width of 22, I'm looking at 1 centimeter removed from each of these. So that would be 22 minus 2. So that would be 20. So when I multiply our dimensions to get my product for the volume, it would be 20 instead of 22 times 14 instead of 16 times 1, which is our new height. So I would just crunch those numbers with my calculator, plug those in, 20 times 14, it's like it'll be 280. So that would be a volume of 280 cubic centimeters. All right, so let's see what would happen if I have a box height of 2 centimeters. So now, instead of cutting out 1 centimeter, the height of this box, this next one that I do, if I wanted to have a height of 2, I have to cut out this corner here. When I remove that corner, of a 2 by 2, then I can fold up these sides. And then we'll calculate that, and I'll have to do that on all 4 corners. So let me do that and I'll show you the result. All right, so I just stopped here at cutting the 2 by 2 edges out just so you guys can see why I need to do that. Then I can fold up each side and you'll see the box forming here. Okay, so if I taped these corners, then I would have my box, and it is a height of 2. It's not the exact same size as the one with a height of 1. It's hard to get the whole thing. It's actually a little bit smaller. It could fit inside of it. So this is going to have a different volume as well, but how will that volume differ? So let's go ahead and calculate that volume. So remember, I started with 16 centimeters here at the top and 22 along the edge. So my new width here, if this side is my edge, I had 22. I removed 2 centimeters here, and I removed another 2 centimeters there. So really I removed 4 centimeters from this whole 22 centimeter edge originally. So 22 minus 4 gives us a new edge of 18 centimeters. Then looking at the top edge, I did have an original 16. I removed 2 from each corner to get this height of 2. So that means it would be 16 minus 2 on this side, minus 2 on that side, so 16 minus 4. So that gives us now a new top edge with a length of 12. And like we know, our height is 2. So now I'm going to calculate the volume there. What do we think will happen? 18 times 12 times 2, and I get a volume of 432 centimeters cubed. Wow, look at that, just height and a height change of 1 centimeter right here. Really increased the volume of that box. Even though it wasn't as wide or long as the other one, that height increase really did help the volume increase. Okay, so let's see what happens if I have a height of 3 centimeters. So let me construct that. Actually, you guys are probably getting to a point now where you're realizing I don't have to build every single box. We can just use our math skills to figure out these dimensions. So if I'm doing a height of 3, remember I'm going to be losing a 3 by 3 corner in each corner of my original piece of material so that I can fold it up. So I would cut those out, and then I would have my new dimensions. So let's stop. Do I need to build a rectangle every time? No, now we are starting to recognize this pattern here. So my long edge here, if I'm cutting, remember I'm cutting 3 out from each corner. So I would be removing these 3 and these 3, which mean my original 22 centimeter edge here, I'd be removing a total of 6 from that. So instead of 22, it would actually now be 16. My original 16 centimeter top edge here, I'm also removing 6 from that, 3 in each corner to get that height of 3, which means now that length is just 10 centimeters. But, so those are shorter, however, my height is now 3 centimeters. So let's see what that volume is going to be. 16 times 10 times 3. Whoops, I did plus. 480 centimeters. So it wasn't quite as big of a jump from 1 to 2, but we do see that we are still getting these larger volumes. Okay, so I just want to pause and recap. So our first box here was 20 by 14 when I removed 1 inch from each, and that's this, and it has a volume of 280 cubic centimeters. Our second box, ignore the number ones, by the way. Our second box had dimensions of 18 by 12 by 2. So it is smaller, but the volume grew a ton because this volume is 432. And then this box has a height of 3 centimeters. And as you can see, they get smaller and smaller. They appear to be smaller and smaller, but that height change is actually making that volume go up. So let's say my goal was to create a space that I could fill with the most sand as I could. I wanted the most sand, like if I'm building a sandbox, then I would want that highest volume. So a height of 3 at this point would be my best bet for maximizing that volume. So let's continue and figure out what our volume is going to be as we continue changing this height. So like we see happen in math all the time, we don't have to continue building. We can now apply the patterns we're seeing to this. So let's fill this in and for a couple more different heights. So with a height of 4, now I'm cutting out 4 inches from each side. So I'd be cutting out, let me zoom in here, 4 inches from every single corner, 4 by 4. So that I would be removing 4 here and 4 here. So really removing 8. And the 22, if I'm removing 4 here and 4 here, removing 8 from that edge as well. So that 22 minus 8, that would now be 14. 16 minus 8 is 8. And now my height is 4. So the volume would be 14 times 8 times 4. For 48, so I see a decrease here. So we went up 280 to 432 to 480 with a height of 3, and then back down to a height with a height of 4 to 448. So it looks like this may be one of our better options. Let's see if this trend continues. So now let's do a 5-inch or 5 centimeter height. That means I'm taking 5 from each corner here, so removing a total of 10. Removing a total of 10 from 22 gives me 12. Removing a total of 10 from 16 gives me 6. And now I have a height of 5 inches. So 12 times 6 times 5 is 360. So now I'm seeing this slope back downward after kind of hitting what we think may be one of the higher options here. Let's do 6 as well. Okay, so now we can speed up a little bit. So if I'm taking 6 from each side, from each corner here to fold up, that would be 12 total. So 22 minus 12 is 10. 16 minus 12 is just 4, but I've got a height of 6. So 10 times 4 times 6, 240. So continue to go down. Let's see, we could continue. Would it make sense? I'm going to jump down here to 9. Would it make sense to have a height of 9? Think about that. We'd have to be removing 9 from a 9 by 9 corner. But that would mean I'm removing a total of 18 centimeters here. But I only started with 16. So not all values make sense. In this case, 9 does not, it's not a practical value. That's an impossible value for the height. Same with 8, because think about our original 16. If I removed 8 on each corner, there goes all my 16 centimeters. And it doesn't make sense to do that. Let's finish with 7 then. So if I do 7 by 7 corners for a height of 7, then I would be removing 14 from 22, which is 8. I would be removing 14 from 16, so it would just have a length of 2, just an itty bitty side there, but a height of 7. That looks like 8 times 2. That's just a volume of 112, so much smaller. So looking at this, it looks like our ideal in terms of whole number centimeter height would be 3. So let's take these points that we just plotted and see what they look like visually. Let's represent this on a graph here. So the first thing here is we want to label our axes. What makes sense to label our axes here? So we've got a height of the box. That's what we chose. That would make the height the independent variable or the input, and that would make the volume our output because our volume depended on the height. So we will do height of box. In centimeters. And we started at 0 and went up to 7. So let's see how much space I have. I'm going to scale by 2s. So this would be 1, 2, 3, 4, 5. Okay, so there's my x-axis labeled, and then my y-axis is volume, and my lowest volume is 0, and I'm going to try and go up to 500 since my highest volume was 480. So I'm trying to do this without moving it too much. So this will be volume, and that's in centimeters cubed. I'm writing over my other work. Okay. How should we scale this? So let's see what our y-axis is. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. All right, if I want to go up to 500, let's see. 100, I'm going to scale by 25s. 200, let's see if I make it. 300, 400, 500, I can stop there. All right, so plotting our points, we had height of 0, volume of 0, height of 1, volume of 280, so 75 right there. Height of 3, volume of 4, or sorry, height of 2, volume of 432. So here's 400, 425, so 432 would be around there. A height of 3 gave us a volume of 480, so 3, 480. So 400, 425, 50, 75, 480 right here. And a height of 4 gave us a volume of 448, so right under 450. A height of 5 gave us a volume of 360. So 300, 350, 360. And a height of 7 gave us a volume, height of 6, 240. And 7, 112. All right. So these are my points on my nicely scaled graph. So what we're going to do now is move on to problem 75, which gets interesting because we want to look at how can we model this. So problem 75 in part B. So in part A, we are going to draw a diagram. One second here. Okay, so in 75, we want to generalize our results. So we want to model the situation so that we can generalize what's happening here. So now we're going to generalize results by creating a mathematical model. Modeling is an important mathematical process. A common way to model is to write an equation using algebra. So part A, we've got a little space on your paper for part A. It says draw a diagram of one of your boxes. So you have that diagram there. Since the box in the diagram is being used to generalize our results, so we want to generalize this to find how can we find the volume for any given height? How would we calculate that? You want to represent any possible input. So any possible height. How could we label the height of that box to represent all possible heights? So what that's asking is, we've calculated how to find the heights for one, or the volume if the height was 1 or 2 or 3 or 4 centimeters, but we want to be able to plug in any value of this height. And how do we represent something that can change, that you can choose, and that would be with a variable. So let's say we called this height, say we just called it h for height. So if I say, okay, using a height of h, how can I determine the volume of this box? So that's what we're going to try to figure out now. So the next part of part A says, determine the length and width of our box in terms of the height, h. So let's think about what that means. Let me go back to my camera here. Okay, so if this is h, and remember, I'm gonna write this a little bit farther down here. Originally, we were talking about a length of, where this long side was 22, and then this shorter side was 16 centimeters. So let's think about, if I say, okay, take a height of h out of that, what I'm going to be doing is taking h away in this corner and in this corner, so I can fold up the edges. So if my h, again, represents height, I'm going to take away that one of those h's from there and one of those h's from there. Just like when my height was 3, we took away 3 from this corner and 3 from that corner. So we ended up taking away a total of 6, or 3 times 2. So when my height is just an h now, and I'm taking away 1 h from this corner, 1 h from that corner, my height, what I'm really taking away is 2 h's. So I'm taking my original 22 and taking away whatever the height is, 2 of those to form my new length of that edge. Likewise, when I look at this length over here, which was originally 16, and I have a height of h, I'm taking away h here and h there. So I'm really taking away 2 h's from the 16 to calculate that length. So that would have a measurement of 16 minus 2h. So now what we have is something that we can actually write an equation for volume now in terms of h itself. So I know my height is h. This length here would be 22 minus 2h, and this side would be 16 minus 2h. So since we know volume is length times width times height, we can just multiply each of these expressions together, and then we'll have an expression for volume of a box for any height. So volume equals h times 22 minus 2h times 16 minus 2h. So now I have this model. So you could say, all right, how about a height of 3.5? What would the volume be? I would plug 3.5 in anywhere I see an h, make that calculation, and then I would know very quickly what the volume is. Okay, so let's look back at our problem. So we're gonna move on. We just finished doing 75 part B, which was coming up with that equation, which we did for volume. So now we have an equation to model volume based on our box. So in 76, we're going to think about the context of this problem and figure out some answers to these questions. So part A is asking, is the domain of the relationship limited? That is, are there some input values that do not make sense? Why or why not? How can you tell with the graph? How can you tell with the equation? How can you tell with the table? So let's take a look at that and see. So we did talk about this a little bit because our domain, remember, is the input. And I said when I was filling out this graph, it doesn't make sense to plug in 8 or 9 because with 8 I would have a height or a length of 0 right here on this edge. So, and it also doesn't make sense to have anything less than 0 for a height because it doesn't make, negative heights don't make sense. So for 76 is asking, is the domain limited? Yeah, domain should probably be limited between values I just explained. So probably between 0 and 8 at the most, because then we would be back at a volume of 0. So let's say our domain, which represents height of the box, would probably be, so x would be, actually we used a variable of h. H would be at least 0 and no more than 8. And that would make sense for limiting and based on the context of our problem. So part B in problem 76, let's see what it's asking. Is the range limited? That is, what are all of the possible volumes or outputs? Are there any outputs that do not make sense? Why or why not? Yeah, there, of course, a negative volume doesn't make sense. The range, negative volume doesn't make sense. So let's say our height or volume would have to be at least 0. And it looks like it definitely doesn't get over 500. We're not sure if this is the actual highest point or not. Just to be safe, we'll just say it's definitely less than 500. So that's our limited range. Part B is asking, or part C is, should you connect the points on your graph? That is, would you have a smooth curve? So can we represent the situation by connecting these points? And the answer to that would be, how would you answer, could I have a height of something between 0 and 1 centimeters or between 1 and 2? Yeah, we could have partial centimeter heights. We could do 1.2 or 1.5 or 1.7. So in this case, yeah, we could make this a continuous graph, and that would help us determine or estimate. If I did have a height of 1.5, I could follow that up to the curve and estimate what that height would be, or what that volume would be. Okay, so the next thing I want to do, I want to stop with the questions. Actually, this might be prompted in the book anyways. I want to look at the graph of this. It says, part D says fully describe the graph, but I want to jump to problem 77, which is, what does our graph, if we use a graphing calculator for this, look like? So let me pull that up for you. Okay, I've got my handy dandy Desmos graphing calculator, and I'm going to graph volume. So I can use V if I want. Desmos doesn't care. So we had H times 22 minus 2H. You can see this forming before our eyes, times 16 minus 2H. This will calculate our volume. Okay, this graph looks funky right now, and I can zoom out, or I can click on this wrench, and let's change my x-axis to what we said our limited domain would be, which was 0 to 8. I'm going to go a little bit less than 0. So let's say I do -3 to 11. And then my y-axis, we said nothing less than 0 makes sense. So I'm going to change that to maybe just -3 so I can get a full. And we said it went up to 500. There we go. Look at this. All right. Now I'm looking at part of the graph that makes sense for the context. That should look pretty nice because that's what our graph looks like. So that's encouraging. And we can find this highest value here. So this maximum little point here says that we would get the absolute highest volume of 480.101 if we had a height of 3.05 centimeters. It's worth backing up here because this function is not a parabola. This would be a cubic function because I have h there, and h there. The total degree of h would be h cubed. So this is a cubic function. But within the context of the problem, these negative values where it goes below 0 here, we could definitely get that with this formula. But it doesn't make sense within the context of the problem because the problem is just representing physical space. So only the positive values matter to us here. So I'm going to stop here. This kind of finishes the lesson on modeling a geometric relationship. So the relationship that we modeled was the height of a box based or the volume of a box based on its height. So you guys will see more problems like this, and they will all kind of have the same feel and patterns as this one. So that's it. Hopefully you guys are all set to do the assignment for this, and you'll get some more practice with this on the closure assignment for chapter 1. Thanks, guys. Sorry this was choppy. I'm not used to recording a Zoom lesson by myself with an activity I've never done via Zoom. So thanks for your patience and understanding. Hopefully this made sense. Email me if you have questions. All right, y'all.